that. Okay, so the topic of today is to obtain the derivative of a curve at any point lying on the curve. So yesterday, the parametric equations can be thought of as one of the methods where you can obtain the derivative on a curve. Then today we are going to talk about another method, if you like, but it's just to me it's not a very important, it's not a very difficult method. It's just another method that allows you to obtain the derivative of a curve. So what I'm saying is that a curve on a two-dimensional plane could be of a form of a functions or a form of an algebraic equation like this one. So x and y here describes the values on the xy plane that obeys these equations. So the blue color line is the collection of all the xy pair of points that fulfill this condition. So that is what we mean by the curve. Right? So the curve could be expressed as a function of in the forms of a function, or could be expressed in the form of these equations. For example, you could also have say x squared plus y squared equals to 1 that describe the circle. That's also another way to describe a circle on an xy plane. Or you could have parametric equations to describe a curve. So given that kind of curve, then what is the dy dx, or what is the derivative of the tangent line on a curve? So we are constantly studying different examples, different methods to calculate the derivative of the tangent line to a curve. So that is one of the things that we're going to do today. So given this kind of functions, can you tell me how to obtain, say, the slope of the functions like this one? So the question asks you for here, say, I think this one asks you to calculate the slope of this curve at a point, arbitrary point that has a coordinate of x. Right? So basically, what is the dy dx of this curve at any point of x, and then what is the slope to the tangent point? So this is one question. Then this is another example. You have a circle, so you're asked to find out what is the dy dx on the circle at the point x equals to 3, y equals to 4. And then you have another situation where you have quite a complicated shape of a curve, which is given by y squared equals x squared equals to sine xy. Then you're asked to find out what are the tangent on any of the point on the circle on this graph, right? So, for example, at x equals to 2, what is the slope at the tangent line, whatever. So, given this shape, it's easy to calculate the slope to the tangent line. Then this is another situation. If you have calculated the slope of the tangent line on any curve, then you can easily obtain what they call the normal line, right? So we will talk about that normal line in a minute. But just basically, given any curve, you can calculate the dy dx or the slope to the tangent line at that point. Say for example, you have this curve, right? So then you can calculate the tangent line, which is this red color. Then a normal line is just a line that's 90 degrees with respect to the tangent line. So once you know the tangent line, the slope of the normal line is simply equals to 1 over the slope of the tangent line. So given the knowledge of the tangent line, it's easy to calculate the slope of the normal line, which is 90 degrees with respect to that. So this is a definitions of normal line. So in physics or in very general situation, it is sometimes require you to not only know about the tangent line, you also need to know about the normal line, right? So normal line is is a line that is 90 degrees with respect to the surface of the curve, and is defined as a straight line that is 90 degrees with respect to the tangent. Okay, so this is another example. I give you a what we call volume of that car. Then this is equation that describes the volume of that car. It plots out the graph that looks like this. Okay, so this is the volume of that car. Then it asks you at some point x equals to 2, y equals to 4, what is the tangent and what is the normal? When we say the tangent and the normal, it means we have to work out what is the slope of the tangent at that point, and also the equations for the tangent. Now, once you know the equations for the tangent at this point, then it is kind of straightforward to calculate the normal at that point. Right? So this would be demonstrated in the next few minutes or so. So this is another example where you are asked to calculate the higher order derivative of a given curve. So then there will be these power rules, which is the generalizations of the previous theorem we talked about. Then this is what we can see. So this is the topic that we are going to see one by one. So the most important thing that I'm going to do today is to demonstrate to you the calculation. So I'll try to go through this calculation if it's not taking too much of time, but basically it's just an exercise. So exercise is just exercise. To me, exercise is what we call a procedural exercise. So I mentioned this sometimes, maybe I forgot when. In mathematics, usually people differentiate the learning of mathematics into roughly two categories, procedural and then conceptual. Procedural means that you just memorize the formula, you look at the equations, then you just mindlessly apply the formula and the procedure step by step, just implement the procedure to get the answer without using your brain. It's possible to do that. You see that equations, I just don't use your brain, use a formula, memorize it, then reproduce the steps, get the answer, then you get the A. So that is what we call procedural mathematics. But if you have only procedural ability that you can only know and memorize formula, that is not enough. That might be enough in the secondary school level, but not at the university level. You need to understand not only the procedure of how to perform the calculation, but also the something more than that, like for example the concepts, the principle, the theorem that allows you to perform that calculations, and the logics between step 1 to step 2, from step 2 to step 3. Okay, so that is conceptual, which is much more difficult to teach. So most students, they just love to have procedural mathematics. So just tell me how to do it, then I'll just do it and get an A. But sometimes it's not enough. So my class sometimes is a bit more difficult, because I not only want to show you the procedure of calculating, but I want to also show you more than that. Okay, but in this chapter, there's nothing more I can tell except demonstrations of a procedure. Okay. Okay, so are you still with me? So if you're still with me, then I'll continue with this example. So for that purpose, I have to switch back to my iPad. Okay, so I pause the recording for this one. Okay, so I'm resuming the recording. So we are now differentiating the equation y squared over 2. So to obtain the dy dx, so finally you want to do something. Finally, you want to have what is dy dx as a function of x, right? So, so to do that, you have to understand that the derivative taking is a procedure, and the procedure is represented by a symbol d, and sometimes we just represent the capital D with the dx. So when you see this d over dx, you must understand it's an operation. Like it's just an operation that you act on something to get something. So you would operate using the operator acting on the left hand side of the equations, and then on the left hand side, on the right hand side also, you do the same thing, right? So you have a what you call a left hand side, and then you have another right hand side. So you will operate on the left hand side with the derivative operator, So when you do it on the left, in order to be fair, you must also do it on the right. So you take the operator and act it on the right hand side of the equations. Then you just summarize and then simplify this slide. So d dx of y squared, so you just apply the chain rule on d dx of y squared. So the chain rule will give you 2y dy dx. I think this is what it is. So this will give you 2y dy dx. Okay, so when I write down this one, I do not show you the detail, but for those who are familiar with the chain rule, then immediately you would know that that is a straightforward result from the applications of chain rule. So the right hand side here is the derivative of a function which is just x. So d dx of x is just equal to 1. So you just rearrange it. Then you have dy dx equals to 1 over 2y. Right. So y is equals to, if you look at this one, y squared is equals to x. So the solution of this is that y is plus minus x, right? So this is solution. So this is equal to plus minus 1 over 2x. So in other words, it says for every dy dx, there are two corresponding values of the x. So at the same point of x, you would have two slopes. Okay, so if you refer it back to the equations, so let me show again on my okay, so this is the graph of that, and we have shown that the dy dx is just equals to this number. I think just now I've shown it. Just now I just showed the dy dx for the slope is just equals to plus minus 1 over 2 multiplied with 1 over square. So this is the slope with have a positive sign, and then it has a slope with a negative sign. For every single value of of the single value of x, let me show this. Okay, so it means for every single value, values of x here, the slope comes in a pairs of number, the positive slope and the negative slopes. So what I'm trying to show you is that this is the original function, our original curve of y squared equals to x, and dy dx is equals to plus minus half over square root of x. So this is the positive slope, this is a negative slope. Okay, so that is how you could visualize the derivative of this curve. So that is quite straightforward applications. Then you have another situations of slope which is given to the equations of x squared equals to y squared 25, and then at the point x and y equals to 3 minus 4, what is the slope of the circle. So in order to do that, let me come back to the whiteboard. Okay, so we have this situation, x squared equals to y squared equals to 25, and again we want to calculate the dy dx. As I mentioned earlier on, I would use d to represent d dx. So I'm going to operate the operator d on the left hand side of the equations, and then I'm going to operate this on the right hand side of the equations. So that is to operate the derivative on the left hand side and right hand side. So the left hand side is to d dx of x squared plus d dx of y squared. So operating d, well, to be more specific, I just write it down in more detail, which I don't have to, but just to demonstrate to you how this is done. So d dx of 25, right? So a derivative of 25 is nothing but just 0. D dx of x squared is just 2x. So then d dx of y squared, according to the chain rule, is just 2y dy dx. So we are almost done. Let me wrap off this part so that I have some place to write my equation. So just rearrange it. So the 2 would get cancelled off. Then I have dy dx as my title equals to minus x over y. So that is the dy dx of my equations. Then I want to calculate at the point x equals to 3, y equals to 4, what is the derivative. So this is quite straightforward. Then you just substitute in the values of the dy dx. I just said that at x, y coordinate equals to 3, 4, then the slope dy dx at the point there, the slope is just equals to minus 3 over 4. It's a minus sign, so that finish up the answering the questions. But it would be best if you could represent the calculations on a curve, right? So it would be good if you can explain that. So we have an equations of x squared plus y squared equals to 25. 25 is 5 squared. So we are talking about a circle which has a circle of radius of minus 5 to 5, right? So this is a circle which is having a radius of 5. And then at the point 34, so the point 34 here is this. Then the slope there is a slope. Let me draw it with a different color. So that will be the slope. Like this slope has an this tangent line at the point 34 here has a slope of minus 3 over 4, and this is correct. Why is it correct? Because by looking at this construction of geometry, it's quite straightforward to realize that the slope, no matter what value it is, you have a very sure confidence that the slope has a the slope must be negative, because it is like this. Like a slope that's positive would be like this. So you know that the slope must have a negative value, and our calculation shows that yes, the slope expression is minus 3 over 4. So that completes the calculation. So before we leave these equations, I just want to demonstrate to you some very straightforward questions, but you always want to, yeah, questions?
I think negative 4. Negative 3 over negative 4.
Okay, yeah, so thank you very much for reminding me that. So it should not be 3 over 4, it is uh, wet, let me check my slides first. So the equations is 3 minus 4. Yeah, 3 minus 4. So it's not 3, 4, but 3 minus 4. So what I'm showing you here is the slope at the equations of 3 over 4. So at equations at 3 and 4. So here the slope is minus 3 over 4. So here the statements that you see on the screen is correct, but the question is about the point at 3 minus 4, but not 3, 4. So I have to jot down the point of 3 minus 4 instead of 3, 4. So 3 minus 4 is somewhere here. 3 minus 4 is 3 minus 4. 3 minus 4 is 3 minus 4 is here. Right? 3 minus 4 is here. So this is a point of 3 minus 4. So let me draw it with a different color. Rub off this color thing. Then I mark it with a different color so that you can see this. So this is a point of 3 minus 4. Then you draw a slope. Right? So this is a slope. And I do not know what this slope is, but the slope definitely must have a positive slope because it is positive. So according to this formula, then the dy dx at the point x 3 minus 4. That is how I write down my answer, right? So it becomes clear that dy dx at 3 minus 4, according to the formula, is equals to minus x over y. X is 3, y is minus 4. So it turns out to be just 3 over 4. Okay, so finally, it is shown that the slope of this tangent line m is equals to 3 over 4, which is true because it is positive. Okay, so that's how I complete the calculations. So the stories that you want to learn from my calculation is that you obtain the expressions of this, then you get some functions, you get some answer. Then when you answer the questions, you will say, now I'm calculating the derivative at the point x equals to 3, y equals to minus 4. Then you got some number. Then you would want to translate that solutions into the form of a picture. Then you show this is a slope. Then this is 3 minus 4, and then you draw the circle. So if you do that, your expressions of your answer become very clear, and everyone who reads your answer would understand. And then it also show to the persons who reads your answer that you indeed understand what you are doing. Okay, so that is the correct way of to answer your mathematics question. So another thing before I proceed on to the next question is just additional sharing. When I mark the answer for students in their test, for example, last time, the students just simply write down what they think is correct, but there's no structure, there's no explanation, there's only formula and number flying here and there, and sometimes just simply write something. Hopefully that when the rubbish that you wrote down could give you somehow get them some free marks, right? Because they do nothing, so just simply write something. Hopefully that you give them some consolation mark. And I hate that very much because it just shows the ignorance of people and irresponsibility of people. If you don't know, just say you don't know, just simply write something. It just means that you are not doing the thing right. So I won't give mark to people who simply write something in the hope to get some consolation mark. Right? So if you understand the mathematics, you should be able to explain your steps, explain your procedure, write it out in a systematical manner. So in my calculation, I always try to show you the correct way of answering the question. Every line you write down, you can explain it correctly. And then sometimes you want to illustrate your understanding by drawing the graph, the circle, indicate that you understand what you're doing. Like for example, you want to answer the derivative dy dx at the point of 3 minus 4, then you write down these statements. That would automatically convey the message that yes, you are telling people you are calculating the derivative of these functions at the point 3 minus 4. Right? So if you don't do that, you just say, okay, dy dx equals to something, 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 without saying that you are calculating the dy dx for the point 3 minus 4. So strictly speaking, this is not correct, right? So you are calculating the dy dx at point 3 minus 4, but not any arbitrary point. So in order to do that, before you slot in the values of 3 and 4, you must specify that you are slotting in this value of x and y at 3 and minus 4, but not simply just write down the answer without explaining it. Okay, so try to learn to provide a step-by-step answer systematically using your own understanding. Now, if you do not know how to do that, then you just start practicing. Even though your step is not correct or you do it wrongly, but it doesn't matter. At least it gives you a chance to learn how to express your steps to yourself. So to me, again, I mentioned this some times ago, in mathematics or in physics, if you understand your calculation, if you understand the concept, you should be able to explain it systematically. But if you do not know how to explain things correctly, you are not understanding it deeply. You only understand it through either rote memorization or just simply memorize it without understanding. So a true understanding of a concept is illustrated in the forms of the ability to explain that concept, at least to yourself. If you understand it and explain it to yourself and you are convinced, then you try to apply it to your friends. You try to explain to your friends, or you explain to your brother in the kindergarten, or your sister in the kindergarten. Now, if you do that, then your sister in the kindergarten understand. That means you have been successful in understanding the concept yourself. Okay, so that is what I want to show you. So let me go back to the previous slide. So we are now going to look at another example. So let me see what example I'm talking about. I'm going to share my screens in. Okay, so the next example would be what we call a differentiations on the form of this very weird looking function y squared equals to x squared plus sine xy. And let's see how you calculate the derivative for these functions. It should be quite straightforward. Again, I'm going to show you my whiteboard. So we have y squared equals to x squared equals to sine xy. So you apply the derivative on the, so this is what I mean. You derive the derivative to the whole thing, the left hand side here, right hand side here. So when you apply the derivative to the left hand side, you get d. So let me call this left hand side. So the left hand side means it's an expression of y squared. So I'm applying the derivative to the left hand side, which is y squared. Okay. So the left hand side is just equal to 2y dy dx. Okay. So then I write down right hand side. So when I write down right hand side, I'm telling you people that I'm referring to this as a right hand side. Then I'm performing the operation of d onto the right hand side. So the result of the operations of part of derivative taking on the right hand side is just d of x squared plus sine xy, right? So this is just 2x plus the derivative of sine xy. So I stop here for a while because the derivative of sine xy could be a little bit complicated. So here on the left hand side, I have the 2y dy dx. So I'll keep this here at the corner and come back to use it later. And the right hand side, I have 2x. Then I have something here which I'm going to calculate on the screens again. So let me rub off this part and try to see if I'm able to calculate the derivative of the sine of xy. So here, calculations of the sine of this one. So derivative of sine xy. So see how I do that. Okay, so d dx of sine xy. Okay, so how you proceed with that calculations? It's a bit complicated, right? No, yes, no. So how do you do that? Anyone who knows how to do this? So again, we would use chain rule. So let's see if I can use a chain rule to do this. So what is this? So definitely this will give you how to use chain rule. So let me call this as u. So u is my x, y, and then I have f of u, which is sine u. So that amounts to d dx of f composed of u. Okay, so that is what I would try to do to calculate that. So let me rub off this one. Okay, so that then allows me to write down equals to d dx of f of u. So that operations of derivative means it is equals to df du dx. Okay, so I have du dx So what is my du dx? Du dx is calculated from here. So d dx of u, which is x and y, right? So du dx is just this operations, which is d dx of xy plus x dy dx. Okay, so that is the expression of d du of du dx. So du dx is just this expression. Okay, then I have another thing to solve, that is df du. So df du, what is my f? F is just sine u, right? So df du is just equals to cos of u, right? Cos of u and du dx, which is just equals to this expression. So let me just substitute the df du. So that would become df du is just the cos of u, and u is just expression of x and y. The whole thing multiplied with du dx. So this is my du dx, which is just expression of y plus x dy dx. So is this expression. So my d dx of sine xy is just this whole expression here. Okay, so I have almost done. So now let me clean up everything and try to obtain a clean expression for my derivative. So I have to make some rearrangement to collect all the expressions of the dy dx in one side, right? So earlier on, I have already got this expression. Let me change the color of my pen. So I got 2y dy dx equals to 2x plus this whole expression, which is cos xy multiply with y plus x dy dx. Okay, that is the equations that are obtained from here, where this triple dot is just d dx of sine xy. So now I have left hand side to contain an expressions of dy dx, and the right hand side also contain an expressions of dy dx. So now my job is to try to extract dy dx on one side, and then just work out what is the expression on the right hand side, right? So you have this dy dx here. So try to do this yourself. I'm not going to do it, just avoid any stupid mistakes on the screen. So you have these expressions, then you arrange it, then you will be able to express a dy dx as a function, functions of x and y. So to obtain the expressions for your f with bracket f and y, means it's an expression of a function that involves x and y. It's just a procedure, right? So it's an algebraic procedure. You just manipulate the equations, throw your cos xy, y, x, dy, dx here and there, then you got it. Okay, so I'll stop for these questions here. I'm not going to proceed, but I'm just showing you the procedure, the main part of the procedure of how to obtain the dy dx for this very complicated equation of y squared equals to x squared plus sine xy. Okay, so then you try to complete it yourself. It should not be difficult. So again, this to me is a procedure. It's a procedural calculation. Just follow the steps carefully. And if I make some stupid mistakes in my calculation, please forgive me. Just learn not to be like me, but just be a little bit more be a little bit more careful. Okay, so that completes the calculations for the discussion for that example. So let me see the next part of the example that we want to talk about. Let's come back to the screens. Okay, so let's look at this part, which is the questions that we're going to talk about, which is the slope. So that is not a difficult thing. I mentioned earlier on, The normal is just a line which is 90 degree respect to the tangent. So if you know the slope of the tangent, then the slope of the normal is simply equals to -1 over mt. That is it. So if you answer these questions, then it should be easily answered, right? So you say you have a curve which looks like this. And this curve is x squared x cubed plus y cubed minus 9xy equals to 0. So these equations describe the blue color volume of that car. If I'm not mistaken, you can correct me. This pronounced as Descartes is a French name. I hope that I do not pronounce it wrongly, but you can always check it out for those who study French. So in USM, you can actually participate in the language class and learn French. Then you can pronounce it, or you ask Google how to pronounce it in French language. Descartes is one of the earliest philosopher of science that is a very important pioneer. I think before the existence of Newton, right? So he is one of the major figure that that appears during the Renaissance, that is before or during the earlier dawn of human civilization in science revolution. So he's also a mathematician. So his name appears everywhere, right? So for example, your Cartesian coordinate, that x, y, z Cartesian coordinate is also named after him, Descartes. So he had somehow this volume, this shape just is associated with his name. He asked the question at the point 24, what is the tangent line and what is the normal line? So the Descartes volume is x cubed plus y cubed minus 9xy equals to 0. And you're asked to find what is the slope of the tangent line and normal line at the curve there. So it should be quite straightforward to do this. Let's just try to demonstrate this again. Okay, so I'll write down that x cubed plus y cubed minus 9xy equals to 0. So again, you perform the derivative on the left hand side, and then you perform the derivative on the right hand side. The right hand side is 0, right? So then you would want to change a little bit the expressions here. Maybe, for example, you just move this towards the x, the 9xy minus x 9 minus xy to the right hand side. Then you become x cubed plus y cubed equals to 9xy. So the right hand side and the right hand side would be then different. So the left hand side, the right hand side is just the derivative of 9xy. So the 9 will always be pulled out. Then you have derivative of xy. So then this is nothing but just a sum of two terms. d dx of x times y is just y plus x dy dx. Okay, so that completes the right hand side. Then now we come back to the left hand side. So left hand side is just the derivative of x cubed plus y cubed. So the first term would be easy. d dx of x cubed is just 3x squared, right? Then the next term is 3y squared dy dx. So this 3y squared dy dx is obtained by taking the derivative of y cubed with respect to x. Then I got this. So when I go from d dx of x cubed to 3y squared dy dx, I am again applying the chain rule. Okay, so that I'm almost done. So so I have left hand side equals to 3x squared plus 3y squared dy dx. Right hand side I have 9. So the factor of 9 can be factored out with a 3. So I have x squared plus y squared dy dx. On the left hand side is equals to the right hand side 3y plus x dy dx. So then you just have to simplify this by collecting the expressions of dy dx to the side. Okay, let me see. I just stop off that expression. So then that is almost done, isn't it? Yeah, I think it's almost done. So these expressions could be just easily shown to be like this. Just dy dx equals to something. So that is equals to, not sure if this is correct. Let's see, let me try it out. Since it's not as difficult. So you just pull out the factor of dy dx, then it is just equals to x squared minus 3y, I think. Then I think divide by, I'm mistaken, divided by y squared, y squared, wait, y squared minus 3x. Now I do not claim that my expression is correct, but this is what I think the answer is. But you don't trust me, right? You just go and carry out your calculation to prove it yourself that by collecting the dy dx as a common title, then you should get the expression for the dy dx for that function. Okay, so I think we have to do this as well. So because we have to evaluate the tangent, so it's not enough to stop here. So assume that my answer is correct. Now let me know in case I make some stupid mistakes. Dy dx x squared minus 3y, and then you have y squared minus 3x. Okay, so I think I might be correct. Now, in case I have done some mistakes in my calculations, you would want to correct me by redoing the expression for yourself. So finally, I got this expression for the volume of the car. The dy dx is a complicated expressions involving x squared, y, and y squared and minus 3x. So that is my expression for the dy dx. So now I have a point at x and y equals to 2, 4. So at equals to 2, 4, then the dy dx is simply equals to some number. Okay, so this number is, I just substitute in 2, 4 is just equals to 2 square minus 3, 4 divided by 4 square minus 3, 2. So that will be 4 minus 12 over 16 minus 6. So that will give me minus 8 over 10. So that is minus 4 over 5. So this is the answer for the deca of the volumes of deca at 2, 4. Minus 4 over 5, that is the slope of the tangent line. Then after you have obtained that, then it will be easily calculated for the slope of the normal line. Okay, so the slope of the normal line, which is defined as m, denoted as mn, is just 1 over the negative slope of mt is just equal to 5 over 4. So that is my answer. Now, by no means, I'm not sure whether my calculation here is correct or not, because I just do it offhand on the screen in front of you. Now, it's not really important that whether my calculation here is all exactly correct or mistaken, because I always make stupid mistakes on the screen. So you can try to carry out these calculations, just to be careful. You just have to be careful to do these calculations step by steps. So I also demonstrate to you with my calculation. Sometimes if you are too too careless, you miss some steps. Your sign may be wrong when you move around the factor from left to right, up to down. then you may displace it. But as long as you are careful, then you will get to the correct answer. Okay, so the slope of the normal and tangent are always opposite. The sign are always opposite to each other. So that is the answer to the volume of the car. Let's see if this is true. So let us go back to the screen. Wait, I have something important on. Someone is calling me. Stop it for a moment. So I'm back again. So that is the, so let me show you the screen. Okay, so this is the screen. So it says that here, what I'm trying to show you is that the tangent line should be a positive number. The normal line should be a negative number. And based on so here the tangent line should be positive. The normal line should be a negative number. So if you go back to my earlier calculations, just a moment ago, so at least the sign of my tangent line and normal line appears to be correct. Okay, so again, I am demonstrating to you after every calculation. If there's a chance for you to recheck the correctness of your answer, you always do this. So in this example, I check the sign by referring to the graph given to me. And I find that yes, the sign is correct, but whether it's actually 5/4 or something else, I am not sure, but you can always check this answer. Another thing I want to tell you is that mathematics is good because whether your answer is correct or not, you can always check and be sure about it. Right? So as long as you carry out your calculations correctly and you follow all the steps, anyone should arrive at the same correct answer. Right? There's no ambiguity about it. That's the beauty of mathematics. Okay, so that is what we have discussed so far. Then let us come back to the next topic. So again, I want to share my screens. Okay, so we have finished this volume. Now this is the second derivative. Let's see if you want to do this second derivative, or maybe I'll do something else. I think let me spend the last minutes to do this second derivative. Then I will record another few minutes of recording to complete the rational power rules in a flipped classroom to complete the next few slides. Okay, so just give me another 1 minute or two to see if I can do this. If not, then I'll just let you go before 11 o'clock. Okay, so come back to my screen. Okay, so let's complete the second derivative of this expression. 2x cubed minus 3y squared equals to 8. So I'm going to calculate this fast. Okay, so the first thing here, when I take the derivative, I got 6x squared. So for the second part, I get 6y dy dx. On the right hand side, I just got 0. Right. So this is straightforward. Just write it down. Then I just make some rearrangement. My dy dx, I take it to the right so that the minus sign become the positive sign. Then what's left is x squared over y. Okay, so that is my dy dx. So now the question is that what is the d2y dx squared? So d2y dx squared is again is just equals to d dx of x squared y minus 1. Okay, so you can write it like that. I usually want to write the divisions of two functions as the product of two functions. So I bring y 1 over y to become y raised to the power of minus 1. So now this is my answer for, so this is my next questions, right? So the ddx has been already calculated, and we are now calculating ddx of y squared. So let's see if I can do this within a minute or two. Do it fast. Okay, we are rushing with respect to time. So here ddx of here. So we have the first term is ddx of x squared y minus 1. So this will give me 2x times y minus 1 plus x squared times 2x minus times ddx of y minus 1. Okay, so that is the expression. So this would be 2x over y plus x squared. Then what is ddx of y minus 1? ddx of y raised to power minus 1 would be minus y minus 2 dy dx. Okay, so now I almost got my thing done. That is ddx of ddx of sorry, d2y dt squared, that is a d2y dx squared, is just equals to 2xy minus x squared over y squared times dy dx. So I think that is the answer, right? So you can leave your expression in terms of dy dx, or you can substitute in the expressions of dy dx. I think just now the dy dx is just expression of x squared over y, if I'm not mistaken. Okay, so that completes the exercise for these questions. So we stop here for a moment. I'll continue to record the other few slides in a flip classroom. Okay. So so the next thing we are talking about here is a new slide on theorem 4, which is a power rule for rational powers of differentiable function. So it says if you have a variable x raised to the power of p over q, where p and q are just integer, right? So p over q is a rational number. When it's a rational number, it means it is p and q are made up of integers, right? So for p and q to be integers, then the derivative of x raised to the power of p over q is just equals to p over q x raised to power p over q minus 1. Right? So this is just a generalization to the previous theorem where p over q just equals to an integer. So now you have a ratio of integer playing the role of an integer in the powers of x. So it's a straightforward generalizations. Okay, so you have to have this theorem 4 before you can take the derivative of x raised to the power of a rational number. Without this theorem, you should not simply just apply the power rules for an integer to a rational of two integers. So, okay, basically theorem 4 is a generalization of the previous theorem for the power of x to be an integer, right? So if n here is an integer, then you can just use this as like this integer, right? Okay, so we have learned this earlier on, but here instead of n being integer, it is just replaced by the ratio of two integer. Okay, so then it turns out that fortunately the replacements of n integer by the ratio of two integer will also allows you to obtain the similar expressions, even though if q is replaced by p P over Q. Okay, P over Q. Now the generalization is actually not quite straightforward. Maybe we will show the proof later. I think when we talk about the definitions of a power functions, the generalization of power functions later. But anyway, at this point of time, just adopt this theorem so that you can use it to calculate the derivative of a x variable raised to the power of a rational number. Okay, so you can also generalize the functions that is the theorem for to shapes given to you. Then you can generalize this. You could make x to be replaced by a function of x. So instead of x itself raised to the power of p over q, you can generalize this to a functions of x instead of just x itself, right? So x is x, u of x is a function of x, but this relationship could be easily generalized. So how we generalize it is like this, right? So what it says here is that if d dx of x of p over q, then this is p over q x p over q minus 1. So instead of x, if you have a function of ux, when ux is raised to the power of p over q, then this is equals to p over q u raised to the power of p over q minus 1 multiplied with the derivative of du. So just add in these terms, then you will be able to generalize the this rule for x power of p over q to this rule, which is the derivative of the function u raised to the power of p over q by adding in this. So if you think about these equations slightly deeper, this is just again the applications of what? The applications of um, applications of applications of chain rule. Okay, so when you apply chain rule, then you get these equations. So that's what I'm saying. The generalizations from these equations to these equations is just an applications of the chain rule. Okay, you promote the function of the function of x p over q to u of x, which is a function of x, to p over q. This is p over q. Okay. So for example, if you look at this one, now this is actually not shown quite correctly. So on the screen, a here actually means d dx of x raised to the power of half, right? So half is a ratio of 1 over 2, right? 1 is an integer, 2 is also an integer. So this is just equal to the factor of p over q, x p over q minus 1. So it's just half, right? So that is this bit for the first part, for the b, for the a. Then for the b part, you have d dx of this. Then again, this is equal to 2 over 3 x 2 over 3 minus 1 is 1 over 3. Okay, so that is for b, and c is the same thing, right? So just straightforward. An application of this minus 3 over 4 is just equal to minus 3 over 4 x raised to the power of minus 4 over 3 minus 1 is just x raised to the power of 4 over 3. Okay, so that is the applications of the theorem number 4. Okay, so there's nothing special about that. Now we need that for us to calculate the other functions of u, which is raised to the power of a rational function. So you can try to look at the theorem number 4. You can perform what we call a proof for this theorem, that is this one. So the proof of theorem 4 could be could be carried out by yourself by going through this. Okay, so the statements of y equals to x raised to the power of p over q is equivalent to the statements of y raised to the power of q equals to x power of p. So this is a slide that tries to prove that. So how do you prove that statements? We want to prove these statements: dx of xp over q equals to p over q xp over q minus 1. Now to prove that, you have to start from an understanding that if you write down the statements of y equals to x p over q, now this is equivalent. Okay, this is equivalent. The three line here means in mathematical language equivalent. Equivalent means that exactly the same. It's the same as you raise to the power on both sides with q, right? So on the left you raise to the power of q, right you raise to the power of q. So y raised to the power of q, you got py raised to the power of q. Then right hand side then is x raised to the power of p over q, x power of p over q raised to the power of q. Side you got p of p raised to the power of p times p power of p minus 1. Okay, so you get these expressions. So let me make some space. So I'm going to carry out my calculations onto the other side here. So I just make rearrangement dy dx on the left hand side is just equals to p over q. So the q on the left hand side is moved to the right. Then the right hand side would have x power of p minus 1 divided by y of q minus 1. Okay, so you just have to be a little bit careful to interpret the y to the power of q minus 1. Okay, so let's see how you do that. Okay, so just let me copy down p over q. So you have p x raised to the power p minus 1 and yq minus 1, right? So yq is this, like yq is just your xp, right? So yq minus 1 is, so let us be a little bit okay, so yq. So yq is expressed as y to the power of q minus 1. So you can bring up the y. Okay. So I'm just rewriting this y power of q minus 1 into the form of yq times y. Okay. So if you think about it, you should be able to understand this. Okay. Then I'm going to continue writing this here. P over q times x power of p minus y. Now what is yq? Now yq according to this expression is just to xp. So here you have x power p, and then you have y. Now here is y, so y is just x to the power of p minus q. So I need more space, so let me move to here to continue my calculations. So just stop off this one. So I'm going to continue on this part, which is this thing. So I'm going to move it here. So I have expressions of dy dx is just equals to p over q. So you have x power of p, which will cancel off with this one. So what is left is x power minus 1. Okay, and then you have x power p over q. Okay, so we are almost done, right? So you have this p over q, x power q, then you have minus 1, then this is equals to this. So this is a proof of the previous statements that if y is equals to x to the power of p over q, where p over q is a ratio of two integers, then dy dx is just equals to this expression. So you just prove it quite straightforwardly. So that is the expressions I want to talk about, the proof. So that finish up the proof for these statements. So then we would learn the last example of performing a differentiations of this. So I think this is not shown quite clearly on the screen. It should be referring to the correct expression should be 1 minus x to the power of 2 raised to the power of 1 over 4. And the second is cos x raised to the power of minus 1 over 5. Okay, so this is cos x minus 1 over 5. Okay, let me come back here. So this is first expression. This is just equals to 1 minus x squared raised to the power of 1 over 4. So if you call this y, then we want to calculate what is dy dx for this expression. And for this part, it is actually referring to cos x raised to the power of minus 1 over 5. The PowerPoint is not shown correctly in the iPad, so I'm sorry about that. Okay, so let us try to see how you do the calculations, which is quite straightforward. So I'm going to use my whiteboard to do the calculation. So let us call y equals to 1 minus x squared raised to the power of 1 over 4. So you can use the chain rule to do this. So now if you are fast, then you can do this quite fast. If you're not so fast, then you have to do it step by step. So maybe I just demonstrate again the chain rule. I call ux to be the inner function, 1 over x squared. And then I define an outer function as u to the power 1 over 4. Okay. So in that sense, dy dx, according to the chain rule, is just equals to d dx of f composed of u. Okay, so that would be just df dx and df du, sorry, df du, and then here you have du dx. Okay, so let us continue from here. So df du is just 1 over 4 u power minus 1 over 4 minus 1, which is minus 1 3 over 4. Okay, this is minus 1 raised to the power of minus 3 over 4. Then du dx is just equals to minus 2x. So that is the answer. So you can simplify this to be minus x over 2 and the whole thing raised to the power of minus 3 over 4, where the equation is just 1 over x squared. So this is to apply the chain rule to the equations. But at the same time, you can also do a better job by using the formula that I mentioned earlier on. The formula that I mentioned earlier on is actually these expressions. That is the generalizations of the rule, right? So if you have d dx of u raised to the power of p over q, then you can just straightforwardly apply this to this equation. So let's just try to apply this rule to see if we can get the answer quite faster. So so we have here a function of u, which is equals to 1 over x squared raised to the power of 1 over 4. Okay, so the formula that we mentioned earlier on, it says this. So here, no, I think this is not what it meant. So let's say u is equals to 1 over, say you define u equals to 1 minus x squared, then we are asked to calculate the derivative of d dx of 1 minus x squared raised to the power 4. So this is nothing but just d dx of u raised to the power 1 4. Okay, so that is expressed the questions of this expression in the form of an function u raised to an power which is made up of ratio of two number 1 over 4. So by doing that, then these questions, okay, these questions that we are trying to solve u. So this is 1 minus x squared raised to the power 1 4. The d dx of this function is now re-expressed into a more convenient form, d dx of u raised to the power 4, so that we can then use this formula. Right, so this formula says if you have d dx of u raised to the power p over q, then you can just write this down as p over q u p over q minus 1 and du dx. Okay, so this is just a repetition of this formula. I just write it now on the same screen so that it's easy for us to refer to. So that is just equals to p over q. So here your p is 1, q is 4. Then what is your u? Your u is just 1 over x squared, and then you raise to the power of p over q, which is 1 over 4 minus 1. Right? So this is just this part. Then you have also another factor of du dx. So u here is 1 minus x squared. So you have a factor here which is d dx of ux. Then it will just give you minus 2x. Okay, so that is the applications of this formula. So you put everything together, then you'll be able to obtain the answer for the d dx of this, just equals to the expression. I just write it down again. It's equals to minus x over 2 1 over 1 minus x squared minus 3 over 4, and then you have an x. Yeah, I think that is the answer. So again, this is illustrations of the applications of this formula by applying it to the functions of 1 minus x squared raised to the power of an index. So next time when you see you have any functions that is raised to a power of p over q, and you are asked to find the derivative of it, then you can just simply apply that formula. So now we have another example to demonstrate to you, which is here. You have cos of x raised to the power of minus 1 over 5. Right? So this is again an illustrations of the application of this formula. So you can here see that the u could be defined as a function of cos x. So you can call u to be your cos x. Like u is a function of x, then d dx of u raised to a power of 5 is just what we are looking for. So we are looking for d dx of cos x raised to the power of minus 1 5. Then when you write this like this, then straightforwardly you apply the formula to be minus 1 over 5 u raised to the power of minus 1 over 5 minus 1 would be 6 over 5, then followed by du dx. Okay, then you can then write down the answer for this is minus 1 over 5. U is cos x raised to the power of minus 6 over 5. Then you have the expressions of dy dx. So let me move this dy dx a little bit slower, du dx. Okay. So then the expression for du dx is just minus sine x. So the minus sign will cancel off this. So that would be an demonstration of the use of these equations or this rule, the generalizations of x power q p over q to function of u instead of x, and apply this to the powers of cos of x raised to the power of minus 1 over 5. So that finished up these sections for the differentiations rule that involve these equations and also these equations.